So it's so great to have Lindsay Nicholson with us. Lindsay hails from Scotland. She's been at the University of Innsbruck now since about 2009, first as a postdoc, but since 2021 as an assistant professor and leader in the ice and climate group. She has a PhD from University of St. Andrews in 2005 in glacial hydrology, and has really become a glacial hydrologist extraordinaire if you follow this field, focusing on climate controls, on glacier volume, boundary layer measurements, numerical modeling, and you'll see some evidence of that today. She's very active in the field with the European Geophysical Union, where she serves as secretary of the Cryosphere section, she's a member of a WMO working group on the status of mountain snow cover, co-lead of the IACS working group on debris-covered glaciers, and lead author of the second Austrian assessment report, among many other activities that she's currently involved with in the field. So it gives me great pleasure to welcome Lindsay. Thanks, Lindsay, for joining us, and I'll turn it over to you.
Okay, hello everybody. Thanks very much for having me. It's nice to be able to join virtually, one of the few advantages. I'm new to the webinar format, so hopefully we'll manage this fine. And what you see on screen is a photograph of the Hintereisferner, one of the glaciers that we study intensively here at the University of Innsbruck. It's been studied for the last 70 years. My title of the talk is about sort of deglaciating the hydrology of these kind of mountain systems. And I wrote expected impacts and uncertainties, but really I found that in the time constraint, I can really only talk about some expected impacts, but hopefully we'll have some time to discuss at the end. Okay. Did my slide advance okay? If not, please let me know, because I wanted to begin by setting these kind of mountain glaciers in the context of the global hydrosphere.
All good.
Thank you. So you guys all probably know this as experienced hydrologists, but 3% of the world's water is fresh water. And actually, I think it's kind of interesting for me as a glaciologist to consider the fact that almost 70% of that fresh water is frozen. Now, a small part of that exists in the ground, the surface of the ground is in permafrost, and the rest is in glaciers and ice sheets. So these graphics on the right are showing the small black section up top. The far top right is the 3%, the rest is ocean water primarily. And then of that, the next bar over to the left shows us a third of this water is liquid in form at the Earth's surface, and nearly 70% is frozen. And of this frozen part, though, it's shared between the two big ice sheets that still survive on our planet, the Antarctic ice sheet containing about 88% of it, the Greenland ice sheet 11%, and all the other glaciers a little bit less than 1%. So that's pretty interesting, because in that kind of context, the mountain glaciers sound a little bit unimportant. On the other hand, they still hold more than 150,000 cubic kilometers of ice and fresh water, and this is equivalent to about a third of a meter of sea level equivalent. When averaged, if we melted all of that water, put it in the ocean, this would be the equivalent average sea level rise over the modern day ocean basins. So kind of this slide says both that they're unimportant and important, but one of the things that makes the mountain glaciers pretty important is not just this third of a meter sea level rise, but that we tend to coexist fairly close to them. Like several mountain communities are quite reliant on mountain glacier runoff, and they form the headwaters of quite a lot of the or the head of all the river water that we use. Okay, there Then I wanted to continue, as this was a kind of general talk, to talk about the mountain glacier system. I don't know, many of you may have studied this already, but in the mountain environment, two things happen with elevation. There are very strong meteorological gradients. Firstly, in temperature, with temperature decreasing strongly with elevation at a rate of about 6 degrees per kilometer. And what this means is it gets colder with height, and so precipitation changes from rainwater to snow. And this is actually fundamentally what allows glaciers to build up. Of course, also with the temperature gradient in the mountains at higher elevation, it's much more amenable for snow and ice to survive. And that becomes less so as we descend the Alpine Valley. So we have this strong elevational variation in the delivery and accumulation of snow that can form glacier ice, and also in its ability to survive. And what that means, if we look at the graphic at the lower left, is the upper part of a glacier is called the accumulation zone, and this is where mass gains dominate over the annual cycle. And at the bottom of the glacier, where it terminates in the valley, this is the ablation zone, where over an annual cycle, more ice is lost than gained. But a glacier in steady state remains kind of the same size. Like the ice doesn't just build up and up and up to infinite thicknesses at the top of a mountain, because this is flowing under gravity within the glacier body. So in this context, a glacier can be seen as a long-term store of water in its frozen form, but it's also a mobile store, like flowing under gravity as a slow conveyor belt. And if we look at the diagram in the top right, it's just showing how the mass exchange varies with elevation over the for a given year. What we can see in the solid black line is the annual mass change, showing again that at the lower elevations we have net losses that I just said, and at the upper zones net accumulation. What you can see in the dotted lines is the pattern of summer and winter change. So as anybody who's been in the mountains, which I'm sure you have, we all know that, like in winter, the whole area receives snow accumulation over the entire glacier system and even below. And likewise, we can understand that in most mountain glacier cases, ablation happens over that whole area as well. And it's just the relative importance of the mass gain and the mass loss that changes with elevation to result in this characteristic imbalance with elevation, which drives the flow. So this variation between what's happening in summer and winter also can be visualized like this over the course of a hydrological year for a northern hemisphere mid-latitude glacier. This is like in the first part, we have our winter. So we have a period, if we look at the green here, this is snow accumulation, increasing from non-zero to a peak, and then into the summer season after this dotted line, reducing to zero in the midsummer to the right of the diagram. And the amounts of ablation for mid-latitude glaciers goes in the opposite sense. So in winter, we have minimal ablation, in summer, maximum ablation. And these two curves together show this blue line, such as in winter, the glacier gains quite a lot of mass, and in summer releases it in the form of meltwater. So in this way, we can really understand the mountain glacier system as a seasonal water storage. And in fact, you can also consider it like a natural dam system in the hydrological sense. It produces seasonally delayed runoff because the glacier stores the water over winter and releases it only in the summer season. And as a result of that, it can buffer extreme drought years and reduce variability quite well. So I think this is somehow one of the main hydrological significances of glaciers in the mountain environment. So we've covered it sort of quite carefully at this stage. Important to note is also that this store changes with the climate conditions. So on the left, the two panels, upper and lower, are showing what happens if you have colder or snowier conditions, so that the total mass gain, the store increases. So this means a buildup of snow and ice in the upper part, and eventually this is transferred to a different geometry, a larger glacier surface area, in fact, by ice flow, sort of transferring that extra accumulated mass in the upper part further downstream. And in the opposite case, if we have warmer conditions or less snow, then the total volume of water stored in mountain glaciers decreases. So I think so far, so sort of straightforward. I think we're all quite aware of this. Indeed, because if we look at not just pictures, but if any of us go to the mountains, these are the kind of patterns of change we see. This is the Pastelte Glacier. It's the largest glacier in Austria, showing its change over 90 odd years. And you can see it used to be a really big, impressive glacier filling the valley, and it's a much sadder beast just now. Likewise with your own Athabasca, a very famous glacier, I guess. Huge changes in the glacier areas over recent decades as a result of ongoing climate amelioration since the last, the Little Ice Age and the last glacial maximum, but also in particular in recent decades, strongly influenced by our own greenhouse gas emissions, creating an environment that really isn't that amenable to glaciers anymore. As temperatures rise, particularly in mountain areas due to albedo feedbacks related to the reduction in the amounts and duration of lying snowfall. And that's partly to do with the that precipitation shifting from solid precipitation to liquid precipitation, which doesn't do the glaciers any good. So in one sense, I always think of the cryosphere as a form of, I don't know if it's right to say a form of like release valve for the planet in terms of increasing temperatures. And with our greenhouse gases, we're really trapping more energy into the planetary system. And one way that that can be consumed effectively is through melting the cryosphere. And indeed, like a recent study from last year, a really important study looking at this over the whole globe, confirms that this is really a global pattern, as if we didn't need that clarifying. But what we see here, just to explain, is for certain latitude, not longitude grid forms, we see indicated in color the mean elevation change rate over the last about 20 years. It's actually 2000 to 2019, so almost 20 years, with the strong reds here being minus 1.5 meters in surface lowering, and going into the blues of any kind of positive, and it's 0.6 is the positive. What you can see when you look at this, in each of the size of the circles indicates how much glaciarized area is in that grid cell. What you can see is overall there's strong mass loss. Pretty much everything's showing red. Even the yellows are glacier losses, and only a few quite scattered blue areas can be seen, particularly notably in the Karakoram region, which has been a hot topic of research, why some of these might be actually gaining mass at a very small rate. But the general picture is that we're seeing this loss of glacier ice worldwide. Another important thing from the same study is the fact that here the colors indicate something different. It's showing the mean elevation change rate in meters per year, meaning that, and these bars are showing a timeline over these nearly 20 years. So what we can see is in many areas, there's an accelerating rate of mass loss or decline of these glaciers, say, for example, in the southern Andes, and also particularly pronounced in Western Canada, actually. Whereas here in Central Europe, where I am, there's a really strong and consistent change rate. I think this kind of means that the glaciers here are well, are disappearing as fast as they possibly can. Yeah, so there's the glaciers are going, and they're going sort of faster than ever. That was really strongly illustrated in the European Alps this year. We've just finished calculating all the mass changes for the glaciers that we monitor. And there are several other groups here monitoring other glaciers throughout Austria, and obviously also scientists from Switzerland and France and elsewhere who do the same for key glaciers that are monitored, benchmark glaciers that they're called, that we monitor to be representative of what the overall change is. What we're looking at here is the mass balance rate, so the mass exchange rate expressed as a thickness of water over the glacier surface, so averaged over the glacier surface. This is actually kind of the same, an equivalent unit to kilograms per meter squared loss, but it's kind of a quantity that's expressed in relation to the glacier's area. And so you see the distribution of the mass balances that have been measured on Hintereisförne, this benchmark glacier that we measure that was in my first slide, over the last 70 years. And you can see that the changes that happened in 2022 are really far outside the envelope of normal mass changes that we've had over the whole measurement period. So we're having some very extreme years now when, for example, almost no snow survives on the glacier. So this net mass loss area covers the entire glacier, and this makes it really makes the environment that the glacier is sitting in completely untenable for a glacier to either form or survive. So that's kind of what's happening, and we expect in the future that this kind of extreme event would be a bit more frequent, unfortunately. So this is what's happening. And so a short way of saying this is, for many mountain ranges of the world, we can say that deglaciation is coming, particularly for the European Alps. This is a diagram from a study, actually replotted from a study that was carried out in 2019, which used some of the most state-of-the-art and high-resolution atmospheric models to force glacier evolution under these three representative concentration pathways, the 2.6, 4.5, and 8.5 scenarios. And you can see that in the 8.5, which is quite close to where we're tracking just now, we lose nearly all the glaciers of the Alps by the end of the century. And this is expressed as a percentage of their volume in 2017, as indicated on the x-axis. I guess what's interesting is the blue line, for example. If we could follow a much more optimistic emission scenario, we could sort of retain about 40% of that volume, which I would argue might be really worth trying to do for the reasons of the role that these glaciers can play in the regional hydrology. So I took these next set of figures from the IPCC report, the special report on ocean and cryosphere under climate change, which was produced in 2019, and it includes quite a few nice schematics, because I think there's no point in reinventing the wheel, and these diagrams are kind of beautiful to explain the net effects of glacier loss on mountain hydrology. So let's just spend a little bit of time looking at this. You can see in the bottom three panels that what we're seeing from left to right across the screen is different states of deglaciation of an alpine catchment. And what we look at first, as indicated towards the top left, is over the decadal timescale. What we see in this sort of projection into the future is in brown that we expect groundwater maybe to stay the same, at least in this schematic. There are other reasons why that might not stay the same if people begin to withdraw more or draw down the groundwater, which is certainly happening in some irrigated mountain areas. Of the precipitation that's falling over time, it's split between the very pale blue and the bright blue, showing the partitioning between snow and rain. We can see that progressively over time, proportionally more of this precipitation is coming as rain and less as snowmelt. And so that's going through time this way. And the glacier meltwater is shown in this turquoise cover on the top, which is showing that over time, as the glaciers recede, there's actually something happens where we get quite a lot of excess meltwater in the stream. And this has often been referred to as the deglaciation discharge dividend, because as the text below shows, it's basically the fact that while the environment is busy removing the glacier, it has to do that by putting the glacier meltwater all through the stream. So we have an excess runoff compared to the normal catchment precipitation and runoff closure cycle as the glacier is retreating. When a glacier is in completely in balance with its environment and not undergoing change, then at the annual scale, the precipitation is distributed. It's seasonally delayed in the runoff, as I said before, but all the same amount of precipitation that's fallen eventually should be delivered at some delayed point to the stream. So this discharge dividend is also related to this concept of peak water, which is basically just discussing the point that when your glacier is retreating maximally, then you reach a maximum of this excess meltwater runoff in the basin. And thereafter, it drops off, as you can see in this curve here. And this reduction happens because the glacier is actually shrinking. There's less glacier to give, to deliver meltwater into the stream. So we can see the rising limb of this turquoise part of the curve between before peak water to the center of the curve being the decline in the glacier, and then once, or it's peak removal, and then after that it's removed until, in this diagram, the glacier is melted away completely, so there's no glacier runoff anymore. This comes along with associated changes in the yearly distribution of discharge in streams, which is this next panel further down. So the colors indicate the same, but we can see here that during peak water, this diagram in the middle, we have like a much higher peak runoff in summer than we did when the glacier was closer to balance. This is when it's in its strongest imbalance phase. But we can also see, once the glacier has melted away, that there's with no more glacier contribution, the peak or the annual peak discharge coincides with spring snowmelt rather than summer glacier melt. So there's a shift in the timing here. Going to even higher temporal resolutions, what this diagram is showing us is, on the left, daytime and nighttime, or sorry, rather, two daytime conditions, a clear sky and a kind of stormy overcast precipitation daytime condition, with the barrier between them, or the divide between them, being nighttime. And really all you need to take from this is that, again, the peak discharges are highest when you have a very out of balance glacier, delivering this high meltwater dividend. And once the glacier is gone, there's quite a stark contrast, because within a glaciated catchment, a strong like summer melt on a very warm sunny day in midsummer delivers a lot of water to the river, whereas in the absence of the glacier at all, this is a substantial difference. And this has effects, of course, on the availability of water in summer within these catchments, and knock-on effects on ecosystems that are dependent upon them. So this is kind of the short summary of what's expected for mountain hydrology in a deglaciating climate. I wanted to mention the fact that this timing of peak water is quite important. Obviously, I'm sure you can all imagine, in the context of water planning, we know that the maximum discharges are changing, and we know that at some point we are going to be experiencing increased water runoff and then subsequently decreased. So the time period that you're basing your planning on is not very, you can't really extrapolate it unless you know where you're sitting on this curve. And this is a kind of condensed or subsampled diagram from the same report. And I'll just explain what we're looking at here, because if we look at the bars, these are showing the percentage of the regional glacier area that hits peak water at a given time point, with time shown along the x-axis. And the left panels that are all in blue are for the representative concentration pathway scenarios, 2.6, and the right one is from, so like the most optimistic emissions scenario in the right panel is the least optimistic scenario. And these are taken from like 14 GCMs in a study that was actually done by Matthias Huss and Regina Hock in 2018, and then incorporated and replotted in this report. So what you can see here in these different regions that I've chosen to show you is the timing of peak water happens at different times through the coming century, or the rest of the century that we're in. And for example, low latitudes are probably past their peak water already. Also potentially in Central Europe, except for catchments that might have a disproportionate proportion of large glaciers, and that's what's shown in these darker colors within the bands. So when we look at the shading of the bands, we can see that for larger glaciers, they kind of reach peak water a bit later. And so that is actually true of like different catchments. And we can see that, say, very heavily glaciated regions such as Alaska are showing peak water discharge quite a lot later than only marginally glaciated mountain ranges such as the Alps, where I am. I guess what we can also see is in some regions, the different scenarios don't make too much difference in the timing, such as if we look at the, look at the Central Europe case, there's a rather similar distribution here. And that's partly because the glaciers here, quite a lot of the glacier volume, up as much as 40%, is kind of already committed loss due to past climate change. And so the scenarios that we, the behavior of the future is maybe like slightly less influential than in some other regions. If we look on the other hand at Alaska, you can see that with the more pessimistic emissions scenario, the worst case scenario, the peak water is actually later. And I think that's somehow a bit counterintuitive, because we think that later for these big impact changes should be better. But of course, in the case of peak water, what this means is, if we look at the more optimistic scenario for Alaska, is that some of these glaciers could re-establish a stable state and no longer be undergoing heavy retreat. So there's a kind of glacier restabilization embedded in that, which means that the peak happens earlier because there's a restabilization, which is actually a good thing. So in this case, an earlier peak means something good, whereas often when we're talking about climate indices, earlier really doesn't mean better. Just reiterating again, this seasonal shift in timing happens when we remove the glacier, and also because of taking away this buffering effect, you can have more pronounced fluctuations in discharge, interannual fluctuations, because this isn't kind of buffered and absorbed by the glacier as much. Now, the relevance of these, the role of glaciers within a given catchment also varies quite strongly from in different climate zones and from basin to basin and ranges around the world. This is now from quite an old paper from 2011. And I'll just show you the legend first here, which is this bottom, this diagram at the bottom. What we see in red is the so-called maximum of the monthly percentage of water into the basin that's experiencing a seasonally delayed effect. So that's a complicated way of saying like how much of the water is held back in the glaciers. And it's represented as a maximum because this diagram is really just showing a kind of index overview. And the gray bar is simply the population within every elevation band of the catchment going left to right along the x-axis, multiplied by this maximum of the monthly seasonally delayed water. So what we can see then in some catchments, like in the Rio Santa, there's a very large proportion, up to 60% of the monthly precipitation is delayed in glaciers, so undergoes delayed release, whereas in a catchment such as the Yangtze, very little, it's much more monsoonal, and there's not really, I think maybe there's even like barely any glaciers contained in this catchment. So very little is undergoing seasonal storage due to glaciers. So this kind of affects how important these changes would be to the total catchment hydrology. And there's one more thing, this index of the population, it's really not a quantitative indication, but it also shows us though where certain population groups might be most heavily impacted by this. So for example, if we look at the Aral Sea, less than 40% of the precipitation is seasonally delayed, but quite a high population is dependent upon that, and so it could have a higher impact. So it's just useful to always think that in some basins, actually it doesn't really matter from a hydrological perspective, maybe what happens to the glaciers. There may be other reasons to keep them, cultural, tourism, ecological, but in terms of discharge, it's not always important if the overall discharge regime or runoff regime is actually much more dominated by precipitation, as in the case of the monsoonal basins, even though there's quite a lot of glaciers in these monsoonal basins in the southern, like on the southern slopes of the Himalaya, for example. So just a summary of the discharge impacts that here, we're about half an hour in, so I've only got like 15 more minutes to chat about the non-discharge impacts. But yeah, we have this deglaciation discharge dividend associated with strong glacier retreat. The timing of this varies by region, depending on the current degree of deglaciation, the projected climate for that area, and also the glacier size distribution within the mountain range. And the timing of peak water also changes with emissions scenarios. And I've put here that often there's an earlier peak in low emission scenarios. And that's true for like catchment by catchment studies as well. And then we have this strong seasonal shift in peak discharge from summer towards spring, so earlier maximum discharge. And this, of course, is expected to have quite a strong impact on planning for water use. Yeah, we lose the high daytime discharge from glacier meltwater in midsummer days, but the relevance of these changes really depends on the hydrological cycle that the glaciated catchment is in. And I think, like, in terms of planning, and I'm not a planner, like, I think the main problem is that all of these changes really bring us to the point where, like, the past really can't be a guide to the future for planning runoff in glaciated catchments. And so people need to use better modeling tools and not just extrapolate from the past. In addition to this change in discharge, there's several other changes that can be expected from deglaciating the mountain hydrological system. And I'm just going to talk about 4 of them. Changing chemistry, here with the example of legacy pollutant release. Don't look at the slide yet because it's quite complicated. So I'm going to talk about chemistry, changes in sedimentation, changes in temperature, and changes in mountain lakes. So I can only do this quite superficially, but I just wanted to raise awareness of it. One of the things that glaciers do, as well as providing long-term storage of water in the mountains, they actually also store the chemistry that's within the precipitation, the snowfall that's being laid down. So, for example, here we can see that, like, over time, this is the concentration of organochlorine pesticides, the OCPs, and the polychlorinated biphenyls, the PCBs, and it's been decreasing in time as long as we have measurements of it in the atmosphere and in snow, ever since we introduced quite a lot of legislation at the end of the 1990s and into the 2000s to ban and limit the use of persistent organic pollutants that are known to affect negatively affect wildlife and introduce nerve damage and infertility and these kind of perturbations, and also can't be handled or removed or recycled by natural systems, and hence the name of the persistent organic pollutants. And when we look at in an ice core, same species, like a concentration, say there's a peak associated, if you drill a core down from the surface, the recent past, to older ice at greater depths, there's a kind of peak throughout from spanning the late 60s towards the 80s in use of these kind of persistent organic pollutants, which were thought very cool when they were first released, and we began using them as pesticides and fire retardants, and everybody thought it was brilliant. We used a lot and then decided it's quite dangerous and restricted the use of them. But what we see in the Glacier 4 field, when we have now quite a lot of this older ice being melted away and released to the stream system, is that there's a secondary peak, for example, being observed in lake sediments. So here's a peak use at the same time as the maximum actual presence of these pollutants in the atmosphere. So this is atmospheric deposition into the lake. And then there's a secondary peak coming out about now, when the ice, or when some regions coming out about now, when the ice from the 1970s, or most of the ice layers laid down in the 1970s, are now being stripped out of the glacier. So this is kind of a delayed release of pollutants that are no longer maybe even being used. And it's quite interesting, I think, because we tend to think of our glaciers as being pristine headwater sources in our river systems and pollution coming in further down. But through this way, and also we see sort of when we use our glaciers, such as ski resorts or so on, they tend to have quite high loads of microplastic pollution, or rather higher than we expect for like a pristine environment. So I think there's still a lot that's unknown about to what extent these concentrations cause damage to the local ecosystems, but it's something else that's happening as we deglaciate the mountain hydrosphere. Glaciers carry quite a lot of dirt. This is a photo of the very end of the Hintereisferner, which looks pretty ugly compared to like what we expect for a beautiful glacier terminus. It's really partially covered in rock debris, and there's a lot of like suspended sediment load. With the discharge, the suspended sediment load is expected to change over time. And also as the glaciers retreat from their moraines, a lot of this loose debris can collapse onto the glacier surface and alter the amount of sediment being delivered. And this has implications for managing like downstream infrastructure, dams, or any kind of constructions around them that may be affected by different sedimentation rates. I don't actually know very much about the impacts of changing water temperatures, except for this one study that I read about and taught about when I was teaching in Alaska. And it's a study, an integrated ecological impact study of climate change on the Alaskan coastal ranges. And one of the most interesting things to me in the relevance to this topic was that when we deglaciate or reduce the runoff of or even increase in this during this meltwater discharge dividend, we change the temperatures of the water. And many species of salmon are sensitive to the water temperature, and it affects their spawning. And obviously in Alaska and probably also in coastal BC, like this, the salmon fisheries are a really important part of the human economic system there. So we know that like changing temperatures alters the survival and the composition of different ecological communities. Finally, I just wanted to mention that as we remove the glaciers, we often also create lakes where the glaciers once were, because the glacier itself erodes the underlying bedrock and can form these over-deepenings. In recent years, there have been quite some advances in the way that we can use models to estimate the ice thickness, which is not a trivial problem, because from space, we can tend to be able to map the outlines of glaciers because they're quite visible, both optically and temperature-wise from satellite sensors. So we can map the outlines, although that also wasn't done until the last IPCC report. So as a community, we were lagging pretty behind to make a comprehensive data set. Subsequently, though, we have used, I say we, I mean the glaciological community has used global glacier models to estimate the thickness of glacier ice. And that can be used then to show where there are really over deepenings or basins formed in the bedrock that's underneath currently existing glaciers. And here's a picture that's just a screen grab of a data set shown around Mount Everest, indicated, labeled in the middle of this picture. And the number of lakes and their extent that is expected to form by the end of the century if these glaciers melt away as we expect, according to our simulations. And so the consequences of this, like it's quite good in some ways to be able to store some water in a dam, in a basin depression. It kind of allows some of this seasonally delayed storage potentially to be recreated in partially natural, partially human modified dams that are left behind. But the problem is that some of these in high mountain areas pose a risk. This is a case study of the Imja Lake. In the bottom, we can see in blue outlined on an air photograph, very small. This lake started in 1962 as very small ponds, and then it coalesced, and by 2013, it's a couple of kilometers long, spanning the whole lower tongue of the glacier. And while at the moment, this lake probably isn't too hazardous, it's been a very poster showcase glacier lake for glacier hazards. It's been subject to a big engineering activity to lower the water level, to increase the freeboard between the water level and the height of this moraine dam that surrounds it, that you can see in the top picture. It's just a natural, the latero-terminal moraines are impounding the water. Historically, it was quite stable because this area that we see to the left of the upper picture downstream, so the glaciers flowing from right to left or top right to lower left, there's this bright blue lake which is disconnected from any overturning, and there used to be like almost a kilometer wide of like ice cored moraine that poses quite a big barrier to any potential outburst triggered by a small wave or calving event into this lake. But now this body is being eroded away, and the dam is becoming progressively narrower and narrower, and added to which the glacier itself is retreating towards the top right of this photograph, which leads it to be much more overlooked by very steep slopes. So there's much more likelihood that snow avalanches or rock falls can actually go straight into the lake and trigger a small psych wave that can then damage the dam. So again, the balance between if these are potentially useful water stores for the downstream community, or if they're potentially hazardous, is quite complicated. And I won't talk about this actually, but welcome questions on it, because I'm kind of in my last slides. But we've communicated this risk quite poorly in the past, to the point where the local communities are split between being oversensitized and very afraid of these lakes, probably disproportionately and inappropriately afraid, to being very blasé because they think the danger has been overstated. Finally, I just wanted to say that the other big hydrological impact, which goes way beyond the mountain hydrology realm, is of course that the ultimate location for water that is being removed from our mountain cryosphere by glacier melt is the ocean. And in the last 20 years or so, glaciers, the mountain glaciers, not the ice sheets, have contributed about 21% of the observed rise over these recent years, which is obviously quite a significant proportion. And that's about 47% more than the Greenland ice sheet and double that of the Antarctic ice sheet. So this is kind of me just looping back to the fact that although this is a small proportion of our frozen freshwater on the Earth's surface at the moment and into the foreseeable future, these mountain glaciers and their loss is remains one of the major contributions to ongoing sea level rise. And this is certainly going to cause humanity some problems, because our best case scenario indicates a mean sea level rise of more than 40 centimeters, and a large proportion of the global population lives by the coast. And additionally to that, this sea level rise isn't evenly distributed. So there are some low-lying, heavily populated coastal areas that will be subject to much higher rates of sea level rise, even in this best case. So I'll close then with a kind of recap summary of what still needs to be done. I'm sorry I didn't really get at all to the idea of the uncertainties, but I do think we need to keep improving and better understanding the uncertainties in our global glacier models, and how we couple them and combine them with hydrological model projection capabilities to understand better what we can expect in specific mountain ranges and catchments. And also related to the third point I've put on this slide, we need to be able to operate these at different scales, because often we need results for an individual catchment for planning purposes. And there's quite a lot of small scale variability, not just regional from mountain range to mountain range, but within certain catchments dependent upon the amount of, or the degree of glaciation at the current stage, and how that's going to develop over time. We also still need to keep working quite strongly on improving the atmospheric projections, specifically for, or especially for, understanding the precipitation and its partitioning between solid and liquid. And a lot of effort is going on just now in the atmospheric climate modeling community to produce higher resolution models, or outputs from higher resolution models that are, the hope is that that will more accurately capture the complex processes in mountain terrain. Yeah, I guess we have to prepare planning for all these changes, not just in discharge, but the knock-on changes in those 4 examples that I showed you. And maybe what we really still need to do is try and mitigate climate change, so we can save some percentage of our mountain glaciers, so they can still do this work for us in the hydrological sphere in the mountains. And with that, I'll stop. Thanks very much.
All right, thank you very much, Lindsay, for a really wonderful overview of this important topic. We have a live audience in the seminar room, and I'm not sure, Tim, if it's possible for some of them to ask questions at the microphone there. We also have an online audience, and I'm looking for questions in the Q&A. I don't think you can access the chat, but you'll see a Q&A button if you're watching the live stream. Tim, you let us know any other ways that questions can come, and I can do that as well. One thing I thought, Lindsay, we've had a couple of very nice sea level rise talks. One was on Jay Famiglietti's podcast, What About Water, maybe a month ago, with some quite alarming numbers, even in excess of what you were describing. And then a couple of weeks ago, John Cherry, noted groundwater hydrologist, recent Stockholm Prize winner, he was giving a talk on groundwater and saying that pumped groundwater from agricultural areas primarily is responsible for about 1/4 of current sea level rise. So it's so interesting, all these different sources when you look at their relative amounts. Well, while we're waiting for the first question, maybe I could ask you one, and that is, I'm often asked how to quantify the glacial melt component of the storm hydrograph in mountainous headwaters. And it seems straightforward, given that the ice is light isotopically and perhaps has some differences in geochemistry, to then use a mixing model to kind of sort that out. But I don't see a lot of clear examples of it in the literature. I'm just wondering if that's something you're aware of, if you've tried, if you're aware of any papers that have tried to get it's not so much the total amount of the hydrograph, but the components of the flow, and really, nailing what the glacial contribution is to that flow. Any thoughts on that?
Yeah, so I've only seen it be done at much longer timescales than like individual storm events, for sure. And I'm not sure if that's just a lack of sampling. Like I think nowadays we can have like, what's it called? Just like inline sampling. So continuous sampling should help make that possible. Yeah, I'm not aware of any papers who try and do it on actually like during individual storm events. And what I also think that we do quite badly with, so another way you could maybe try and tackle it is by having a glacier, running glacier energy balance models to say, okay, I have this much precipitation, but then what's happening to the glacier melt? But actually our energy balance models are pretty bad at that. Like, hands up. We often tend to ignore the effect of precipitation. So not even including like the sort of heat that's delivered with precipitation onto a glacier, although we do tend to account for phase change heat release. And we don't really count for any sort of real frictional effects of like precipitation, really hard precipitation, for example, onto glaciers. And there would be nothing really to stop that from being done. But to my knowledge, it's not been done. So I would say that like over very high temporal resolutions of like individual precipitation events, there's some scope to kind of try and improve the application of a model, which would let us see what we expect in terms of the energy available for melt under these circumstances.
Right. Okay, thanks. There may be a question in the room. Yeah, go ahead.
Here's a live question.
All right.
Hi there. Thanks for a great talk. I'm kind of interested in the potential effect on winter base flow going into rivers as a result of deglaciation. And I wonder if you could comment on that. Thanks.
Yeah, so I was just writing a note, sorry. Well, actually, I don't think I do know much about that. I mean, maybe you have some, do you have some suggestions for me, or what I could maybe comment on your own thoughts on it? So we can have a discussion about it, because glaciers, because of the overburden pressure of the ice, they can have liquid water at their base during winter, which I guess is unexpected. So I would imagine that under thick glacier ice, you can have recharge of groundwater. I'm not very sure how much that is true for mountain glaciers of the size that we have in the Alps. Quite possibly it's very relevant for glaciers the size that are existing in Alaska, and it's certainly relevant for like the ice sheets. You can have liquid water recharging any basal, any groundwater. But tell me what your thoughts are. Maybe I can say at least if that's reasonable or not.
I'm not an expert either, but what got me interested was seeing those small lakes forming where the glaciers used to be, and I wondered if that would be contributing to groundwater to perhaps support base flow as the glaciers recede. And the other thing I thought about was a slight upliftment as the glaciers recede, as the Earth's crust goes up slightly, if that could have any sort of impact as well. Those are the thoughts that came into my mind.
Yeah. So in generally, I think that the lakes that are forming in basins that are almost like quite intact bedrock, we would say. So I don't know, like if it's I don't know how likely it is that we get good infiltration through these lakes and ponds. And also, if you think about like the kind of sediment distribution of like these glacier meltwaters, there's likely to be quite an intact bedrock, as it's been like very scoured by the ice itself, and then kind of lain inside with very fine silts. And again, like this is not something I know about, but I think that would be quite a good combination to make a fairly impermeable layer. But I don't know, like it certainly could be a contribution. And what might be interesting is if this, so people are really starting to look now at the groundwater fluxes in high mountain catchments, and looking exactly at these processes. So your question's really topical. I was at the International Mountain Conference like last month here in Innsbruck, and there were really many talks in sessions about looking at the groundwater recharge. And I guess this is because people are looking to see if there's some compensating effects to be expected there. But I'm sorry, I actually can't answer really what the current state of the art is on that.
Thank you.
Other questions, live or online? We've got a new format this week, Lindsay, so we're working through how to handle questions, given this is the first time we've used this particular medium. I guess, following on from John's comment, there could be kind of downslope subsidy where those headwater, augmentations in groundwater could then play out in extending or increasing base flows in parent watersheds farther downstream. One thing I was wondering too was, in catchment hydrology generally, we have this mismatch between our perceptual models of how headwaters store and release water, the age, the flow pathways. I suppose that's true in glacially dominated headwaters, and how you deal with that complexity in numerical models, which are, by definition, extreme simplifications of a lot of things we don't even know the physics for, preferential flow and other things. How is that being grappled with in your field in glacial hydrology?
Yeah, great question, because on the glacier, on the glacier itself, we do appallingly with glacier storage, water storage, I would say. We calculate a proportion of water that can be in the glacier at any point that refreezes, but we have a very poor grasp on the transfer times of meltwater through this crystalline medium. And to my knowledge, most of the surface energy balance models that would try and treat melt in a complex way like that, it's kind of like where it's melted on this grid cell on the glacier surface, a proportion is retained and could refreeze, and the rest is just like taken straight to the river. So we don't actually have a good downflow transfer or reabsorption later at a later like downstream stage in most of the models that are used. These global models that we use to calculate like glacier change don't resolve these kind of processes generally at all, but that's, I think, reasonable for the kind of timescales that they're applied over. They're mostly running at monthly timescales for multi-annual simulations. I also think that it's true, as far as I know, like when we're combining glacier effects in mountain hydrology models, we still just, so it's rather similar to what's done for different terrain elements, that some kind of retention or transfer behavior is assumed. So I think there's quite a lot to be won there, but I do think I'm not sure like the best ways to begin, because we would need modeling of a complexity that's really like hard to grasp and hard to implement practically, or some very good field studies that require also quite complex instrumentation to try and grasp what's going on.
Yeah,
I think both are real challenges. And what's difficult is you'd think it would be one of these problems that we could look at as a residual, but then we have to be very competent and confident about what errors we have in our existing models.
Yes.
So I think it's really a knotty problem. Yeah.
One last question. This is online. For hydrological modeling, we typically simplify the simulation of ice dynamics using like VA scaling to focus on the simulation of runoff processes. But reviewers from glacier backgrounds would request more complex methods for glacier modeling. How would you treat this issue? I don't know.
Thanks for the question.
Yeah.
Yeah, I think it depends a little bit on what like hydrological model you're using. And I think you're right. Like until recently, like even we in the glaciology world only use this volume area scaling. And so what this means is saying like how big the volume is of a glacier or its area by a calculated mass loss. So you can either scale the surface area by a known runoff amount to say, okay, this is how the glacier is shrinking. So what we do in our research group here just now, and my colleague Fabian Mosion is one of the lead developers, but it's a whole team of people for a global model called the Open Global Glacier Model. And it's a modular thing. And so they actually incorporate quite a lot now of tools to provide and calculate runoff. Now that's not like directly integratable perhaps into sort of different approaches of hydrological model, for example, like planning models that kind of have like nodes and connecting points, and you have to have like certain amounts of runoff there. But now the latest generation of regional glacier models actually incorporates a more complete evolution of how a glacier's geometry adjusts as it melts under a changing climate. So I guess there's two ways to go. One would be to do maybe for your region or whatever you're applying a brief comparison with a model such as that, which I think would be quite possible through collaboration and so on, or even there's quite good guides for these kind of models now online, and then see how your volume area scaling that you're using in your model like compares to a more complete one for a couple of case studies, and then either continue if that looks good, or of course like do some comparative studies with whole glacier dynamics models. I still think we're not capturing the full complex glacier dynamics, but it's a, you know, science, it's an advancing process, and it's really much better what we do now with our global models than we did even 10 years ago, both the input data sets we have and the processes that we capture. So we're making progress all the time, and I would hope that ultimately we can really couple the glacier and the hydrological models in the future in ways that are productive for answering both questions. Yeah.
Good. Well, that's a hopeful message to end on, Lindsay. So on behalf of the online, in-person, and those that are watching the recording groups, I'd like to thank you for a lovely talk. And we will see you in 5 minutes on the Zoom address I sent you by email. And for those that are interested, and I hope some will, we'll have an early career discussion with Lindsay that will start in 5 minutes. And it's on a Zoom address that's been sent to all online participants. And Tim has a copy of that for those in the room if you want to go and join that.